Okay, let's take a look at the quiz and see how we did. Quiz 5 is solution preparation. Okay, how many grams of sodium chloride would be needed to prepare 250 milliliters of a 0.5 molar solution in water? And I give you the formula weighed at 40 grams per mole, and the purity factor of the solute is 1.000. Well, using the formula for calculating mass, if you were working with a solid reagent and its mass in grams is equal to molarity that you want times the volume in liters times the formula weight of the reagent divided by the purity factor. And so the molarity we're looking at, let's just bring it down here. Molarity you'd like to have is 0.50 molar. You want to prepare 250 mils in liters divided by 1,000, which gives 0.250 liters, and the formula weight is 40 grams per mole. And that's divided by purity factor of 1.000. No units on the purity factor, it's 100% pure. This gives us 5.0 grams Cl. Okay. Basically, dilute 5 grams NaCl up to, but not to exceed 250 milliliter total volume. And that's a choice in the answer selections. Question 2, how many moles of sodium chloride are there in 25 milliliters of 0.50 molar aqueous solution of the sodium chloride? Well, from the definition of molarity, is defined as moles divided by volume expressed in liters. So solving the expression for moles is equal to molarity that you have times the volume expressed in liters. So in this case, we have a molarity of 0.50 molar times a volume of 25 mils in liters is 0.25 liters, and that is 0.0125 mole and a Cl in the solution. That is, again, a choice. All right. For number 3, how many milliliters of hydrochloric acid, 37%, would be needed to prepare 500 milliliters of a 0.5 molar aqueous solution? And using the formula weight at 36 grams per mole, concentration purity factor 37%, specific gravity given to be 1.14. So using the volume milliliters needed, we have molarity desired times the volume expressed in liters times the formula weight again, divided by the purity factor, concentration of the stock, times the, divided again by specific gravity. So the molarity we need is 0.05, so we start 0.50 molar, sorry. We're asking to prepare 500 mils, so that'd be a 0.500 liters, and the formula weight is given 36 grams per mole. And now that's divided by purity factor, 0.37 decimal fraction, and specific gravity of 1.14 or 1.14 grams per milliliter, because the solvent of the concentrated sulfuric acid is water. We can use specific gravity in the form of density. Well, that works out to be 21.3 milliliters of HCl 37%. Now, in the preparation of solutions, note, add 21.3 milliliters of HCl 37% into less than 500 milliliters of water into a smaller quantity of water, less than 500 milliliters. I'd use 300 milliliters. Anything less than 500. Then, after mixing, add water or solvent, up to, but not to exceed 500 milliliters. Assuming you're using a volumetric flask, then it would be up to the 500 milliliter marker. That is B choice for number 3. Number 4, what is the molarity of a solution prepared by dissolving 36 grams of HCl into enough water to form 1 liter of solution? And we're given the formula weight of HCl to be 36 grams per mole. So basically, molarity is moles divided by volume of solution expressed in liters. Moles solute divided by volume of solution expressed in liters. So in this case, we have moles, we got 36 grams, and to convert grams to moles, we divide by formula weight. So we'd have 36 grams divided by 36 grams per mole, and then that divided by the volume of solution, which is 1.0 liters. Grams drop out, 36 goes to 1, and so we have 1.0 mole per liter, and which is 1.0, well, I'll go ahead and write moles per liter, which is 1.0 molar solution. And that is B choice. For number 5, let's take into account mixing an acid and a base solution. If 25 milliliters of a 2 molar sodium hydroxide solution is mixed with 25 milliliters of a 2 molar hydrobromic acid solution. After mixing, which compounds of the following neutralization reaction remain once the reaction is completed? So we're mixing hydrobromic acid with sodium hydroxide to produce sodium bromide and water. So here are your options right here. Now, when considering a problem like this, looking at the reaction, we see it's a 1-to-1 reaction ratio to produce salt and weak electrolyte. So we take the reaction HBr, aqueous, plus the sodium hydroxide, aqueous, and calculate what the mixing ratio is to produce sodium bromide and H2O as liquid. Now we've got 25 milliliters of 2 molar HBr plus 25 milliliters of 2 molar sodium hydroxide mixing together, and this is 0.025 liter. Let's do it this way, just 0.25 liter times 2 molar gives you moles HBr plus 0.025 times 2 moles of sodium hydroxide. And so this gives us 0.050 mole of HBr mixing with 0.050 mole of NaOH. So in this case, equal molar amounts would leave only the salt remaining. So the only remaining compounds is sodium bromide in solution. Of course, new water is produced, but that doesn't, we're not taking that into account. So only sodium bromide is left in the solution. Now, to expand on the neutralization problem just a little bit more, let's look at it from a practical standpoint. Let's say that we have a base in a burette, and in the case of this, say NaOH, and in the beaker we have an acid, red dots, say HBr. And so what the intent is to add some of the base into the acid and neutralize it. Now we are looking at adding sodium hydroxide, aqueous, into hydrobromic acid, aqueous, and when we do, we produce sodium bromide, aqueous, which is a salt plus the weak electrolyte, in this case water. So we want to add one of the blue in, so what we'll do is drop one of the blue. When we do, one of the red dots turns to an acid, to a salt, excuse me. And then we want to add another one into the acid, and so we have another one. Now the solution is still acidic. The limiting reagent is the base. Once it's neutralized, we still have hydrobromic acid. Now we want to add another drop or so, some more of the base, and so we are at the halfway point. So we have half the molarity as we had. And so we drop another one, and we continued this until all of the base has neutralized all of the acid. Now we've still got some base in the burette, but at this particular point we have a neutral solution. So equal moles of base neutralize equal amounts of acid. So, or according to this, 1 mole will neutralize 1 mole. If we add any additional base into the solution, right here, then all we have is a basic solution. It doesn't react with anything. If we add another one, we have another, and then we continue this, all we have is an increasingly basic solution. If this is examined on a titration curve, we start with a plot of pH before we start the addition of base or the titration, and then we examine the change in pH as we increase the amount of base being added. So we say we hypothetically start at a pH right here, say of 1 or so forth, and then we add a quantity of sodium hydroxide. Well, it's going to get a little, it's going to neutralize some of the acids, so we'll be there. And then if we add some more, we'll continue to neutralize the acid, and then it'll reach a point in here in which it will start going up very quickly. Let's try right in here, and then we'll go up to right here, and then we'll start leveling off about here, and then we'll show a trend as shown here. So the reaction proceeds to neutralize the acid in the beaker, and as it does, the pH increases until we go through what is called the equivalence point, and this, in this case, for strong acid, strong base, would be a pH of 7. Only salt remains in beaker. Okay, now there's another story of why it remains at 7 and doesn't go through hydrolysis. Some of the substances that could be used as an acid may be neutralized, and their anions react with water through hydrolysis and will shift the pH up. Or if you had a strong acid into a weak base, it could possibly shift the the equivalence point down into an acidic range at the equivalence point. But we're working with a strong acid plus strong base neutralization reaction, and the equivalence point will be at a pH of 7.